Thank you, Professor.
No problem. Have a good day.
Question for the homework.
Sure.
Is it okay if you type the first part of the
Yeah.
assignment?
Yeah, that's fine.
Yeah, did I type this?
Yeah.
Thank you.
Mhm.
No. That's okay. That's.
All right, it's 7 o'clock. Let's go and get started. Evening, everyone. How's everyone doing today? Good, doing good. All right, so we're week 3, and so it's an ANSYS week, and so we're not doing ANSYS today, but we are going to do ANSYS on Wednesday. So Wednesday we're going to do activity 2, and so activity 2 we're going to be building on the stuff we learned in activity 1. But as you'll start to see, over the next couple of weeks, we're going to be talking about kind of all the basic kind of components of ANSYS and all, kind of every step that we did along the way. And so what you'll see is that today we'll be lecturing on meshing as an example, and then next week we'll start talking about boundary conditions and material properties, and we'll be factoring in a lot of those lectures into our activities as we go. And so, we're kind of in that first phase of the course, we're still kind of, we're still kind of introducing kind of the idea of what finite elements is, and kind of doing our babies first and second ANSYS activities. And so, we'll be working on that for the next few weeks. And then after that, we'll be kind of doing some more advanced stuff. And so for those of you who are coming in with some FEA experience, I know the first part of the class is going to be a little bit slow, especially for those of you who have had me for an FEA related course in particular. But I promise you, we are going to pick things up once we kind of get past the basics. Okay. All right. So I think that's all my announcements. Are there any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. So the topic for today is going to be meshing. Okay. And so in particular, we're going to be talking about meshing, what I call meshing basics. Because in reality, meshing is it's a very deep topic. It's probably the most, probably the most that we can talk about in this class in terms of ANSYS. And so there's a lot we can talk about with meshing, and we are going to revisit it kind of several different times in the semester. But I think just for kind of this first part of the class, I would talk about just general what meshing is, what the purpose of it is, what are we looking for in the mesh, just so that just to kind of help us with our first few activities. Okay. All right, so first let's define what meshing means. And so meshing, the act of meshing in a finite element context is to take your complicated geometry, your complicated CAD model, and break it up into a bunch of simpler geometries. Our question. So is there any way we can have access to the activity one solution? Oh yeah. I would need to post it, but yeah, I'll go ahead and do that. I'll do that first thing tomorrow when I come to the office. Yep. Okay. All right. All right, so meshing, I'm just going to do a 2D case here just because it's a lot easier to draw in 2D. And so let's say we have a complicated kind of geometry that looks like this, okay? And so to mesh it, we would take this geometry and say, this is kind of a weird shape. We don't know how to solve equations on a weird shape like this, but we do know how to solve it on simpler shapes. So if we break this geometry up into a bunch of little tiny squares, okay, that becomes a lot easier to solve. Okay. And so where meshing kind of gets its name is that by doing this act of breaking up a geometry into simpler shapes, visually what it looks like is that you're kind of putting a meshed grid on top of your geometry, kind of making that part of it. Okay. Okay. And so the reason we do this, is that the finite element algorithms, or the algorithms that are kind of programmed into the computer, they work on a way such that you solve the governing equations on a geometry with a fixed orientation. Okay? Okay. And so it's almost, you can almost consider it as like hard coded into the FEA code. So, the FEA code, they know how to solve, the structural equation on a square and a triangle. Okay. And it's kind of designed to do just that. Okay. And so basically what the FEA algorithm says, if you can get the geometry into a situation where you have a bunch of triangles, then what it will allow you to do is that it'll allow you to solve for the solutions onto those triangles. Okay. But that's the reason we do that. And so in order to get the
Dr.
finite
Tron,
elements,
I have a question.
you need to have, you need to break it up into these fixed shapes. And the process of breaking up into the fixed shapes is called meshing. Okay. Okay. And so now, the next question we need to ask is,
Hello,
now that we
Dr.
kind of
Tron?
know what meshing is and why we do it, what makes a mesh kind of better than a different mesh, right? And so, this obviously what I've drawn here is one way to mesh this geometry, but we could have easily drawn the grid lines, maybe further apart, maybe closer together, maybe we can have different shapes like triangles. And so, there are literally an infinite number of ways to mesh a geometry. Okay. And while there's no such thing as a perfect mesh, there are some meshes that are better than others. Okay? And so what we're going to be talking about today are just kind of some of the basic indicators that tell you, what makes a mesh better than another one, what you're going to be generally looking for in a mesh, and just so you can kind of get started with that in analysis. All right. Any questions on this so far? Okay. And so the next section is going to be titled, what exactly makes a good mesh?
Hello, Dr. Tron, can you hear me?
Very loaded question, but I think we can give this kind of a very simple definition. Okay? And so simply put, I think what makes a good mesh is one that will produce an accurate finite element simulation result. Oh, sorry about that. Yeah, I think it's been mute since last week. I don't know. Oops. Yeah,
Hello,
I haven't
Dr.
been able to
Tron.
get any kind of microphone output since then.
It sounds good.
Sorry about that. Yeah, if you want to type your questions in the chat, then that's kind of the best
I
way.
appreciate you guys trying to help me out. That's very nice.
Check my
of you.
audio settings, speakers. Can someone try speaking? Maybe see if that works.
Hello, Dr. Tron, can you hear me?
Okay. Yes. Okay. I just had to switch the speakers. So
Yeah. I was trying to speak up, but I just want to say thank you to my classmates online in Zoom that got your attention. I greatly appreciate it. That's very nice of you. What I was trying to ask is, in general, so from my understanding is we have two options to do a mesh
Yes.
with triangles and squares, correct?
For 2D, correct.
Okay, so in general, which method is more affordable, more preferable for engineers, the squares or the triangles?
Yeah, we're gonna go through that today.
Oh,
So
okay,
we're gonna go over kind of all aspects of the meshing, from the size to
Okay.
the shapes,
But
and all that stuff.
is there like a general preference? Like most engineers usually use squares, most engineers use triangles, or it all depends on which
Well,
on
we'll get to
the
that. So
scenario?
we're definitely going to talk about all that.
Okay,
Mhm.
sounds good.
Yeah. The kind of the short answer is that it kind of depends on the situation.
Sounds good.
Mhm. Right. So what makes a good mesh? And so a good mesh is basically something that will produce a simulation that is as accurate as possible with the least amount of cost as possible. Right. So it kind of sounds like you're shopping for laundry detergent, right? So you want to buy the laundry detergent that'll get your clothes the cleanest for the least amount of cost, right? But that's kind of what it ends up being. And so, I've kind of underlined two words there because I want to kind of focus on those and kind of how your mesh kind of influences the accuracy and how it influences the cost of your simulation. Okay. All right. So let's talk about accuracy first. And so when we talk about accuracy, what we refer to is basically how closely your finite element simulation kind of reflects or emulates the realistic situation it's trying to simulate. Okay. And so the more accurate your finite element simulation, the more closely it's going to reflect reality. So generally speaking, in order for FEA to be useful, in most situations, you need to have a certain degree of accuracy. Okay. Okay. In most situations, if you're trying to estimate, let's say, the stress in a structure, and your FEA simulation gives you completely wrong results, then that's not going to be that useful. Okay.
So, Dr. Chan, I have a question.
Sure.
So, what the example you just mentioned, would the engineer have similar values to compare their FEA results, whether it be theory equations or experimental?
Yeah, no, it's a good question. So, when you're first kind of developing a code, you do certain tests called validation tests. And so in those situations that you do have kind of a real situation where you're trying to emulate exactly in simulations. And so in those cases, that kind of situation happens a lot when you're developing code to make sure that the code that you're writing actually, reflects reality to a degree. In most practical situations, you're going to be using FEA in situations where you don't have that.
Yeah, that's exactly what I'm thinking. What
Right.
happens if we don't have data to match our FEA results? What do the engineers do?
Exactly. Yeah. So in a situation where you don't have the data, you're kind of putting a lot of trust in the FEA to do that, but to give you the accurate results. But then there's still a lot of tests that you can do kind of outside of that to make sure that certain kinds of errors that you normally see in FEA are not going to be present. So we're going to talk about something called a mesh convergence test, and so that's a test that you can do without any real world data to kind of show that your simulation results are as accurate as they can be for your mesh. And so there's kind of
Very
tests
nice.
like that to kind of test to see, you've at least eliminated a lot of the sources of common error in FEA.
Sounds good. Thank you, sir.
Right. And so how does the mesh affect your accuracy? And so generally speaking, the smaller your elements are, the more accurate your simulation is going to be. And so the smaller you make your elements, generally speaking, the smaller you make your elements, it's going to increase the amount of elements in your mesh. Okay. And so as the element size goes down, then you can expect the accuracy to go up. Okay. All right. And so the reason for this is that, when you run an FEA simulation, what FEA is doing is that it's forming an approximation for what the solution is going to look like on that element. Okay. And so by reducing the size of the elements, by making the elements smaller, you're basically reducing the amount of approximation that it has to do. So in other words, to kind of sum this up, from an accuracy point of view, you want smaller elements because that's what's going to give you a higher quality or higher, a more accurate simulation. Okay. So accuracy is kind of the first, I would say, the first main consideration to make when you're making your mesh. Okay. The other consideration to make is cost. And so by cost, I don't mean financial cost, although you can kind of interpret it in that way. Okay? By cost, what I mean is it's mostly time and memory. Okay. And so generally speaking, as the elements get smaller in your FEA, okay, or in other words, as the number of elements increases, the cost will also increase. Okay? And so if you remember from the first activity, one thing I had you do for each mesh was I had you log down, how many elements are in the mesh, how many nodes are in the mesh. Okay. And so that right there is kind of an indication for how expensive it's going to be. I will say that, for a lot of the simulations we're going to do in this class, you're not really going to notice a difference in the cost. And so you're going to run a simulation on, maybe like a 5,000 element mesh, and then you run the same simulation on 15,000 elements. You're not really going to see that big a difference. It might be a difference of like, 30 seconds or something like that. Okay? And so that may seem insignificant, but for a lot of practical cases, when you're looking at meshes with element counts in like millions or even tens of millions or hundreds of millions, then that's where cost really starts to become a factor, because you're talking about a difference of maybe maybe your simulation finishing in 5 days versus, 3 weeks. And so that really becomes an issue. Okay. And so we have these kind of two factors that you're considering for the mesh. And so one is accuracy, the other is cost. And if you'll notice, these two factors are kind of competing. Okay. And so from an accuracy point of view, you want to have smaller elements, you want to have more elements because it's going to produce you a more accurate solution. Okay. But on the other hand, you have this cost consideration where you don't want to have too many elements. Otherwise, your simulation is going to take forever and you're going to blow up your computer. Okay. And so oftentimes, cost and accuracy are kind of opposing considerations when you're doing an FEA simulation.
Dr. Chan,
Yep.
do you think costs will continue to be a major increase in FEA, even though computers are getting more powerful with time? Do you think that will still be an influencing factor no matter what?
Yeah, no, it's a good question. I think it's one of those things that, as computers start to get more powerful, then you're going to start to want to have more accurate simulation. So it's kind of like a demand and versus availability of resources, because because if you kind of follow the finite element literature and just the computational literature in general, there are tons of algorithms out there that people have developed that just are not practical right now, just because we don't have the computers to solve it. But once we do have the computers available to that, then we'll start to use those algorithms, and then it's kind of like a rat race. And so as computers get better, then we just use more powerful algorithms, and it kind of just keeps continuing.
I see.
I think it's going to keep continuing like that for a very, very long time, because there's a lot of problems right now which people think are unsolvable because they don't think that the computer power is enough. But the computers will get there eventually, and then we'll just come up with more problems that are unsolvable. And so it's a never-ending cycle.
It's a huge area for research. Sounds good.
Yes, for sure. Yeah. Mm-hmm. Okay. Question? Okay. And so, the question is, if these two are opposing considerations, then, what is, how do you find the balance between them, right? So obviously you can't have a very, very accurate simulation, because then that's going to take too long. But you also can't have a very, very cheap simulation, because then that's going to have no accuracies at all. Okay. So how do you kind of balance these? Or where do you find the right balance? Okay. All right. So we'll talk about this a lot more kind of later in the course once we talk about kind of verification and validation. But a very common test that people run whenever they're doing any kind of practical FEA is something called a mesh convergence test. So I don't want to write down too much about it, just because it's not going to be really relevant until later. But basically, with the mesh convergence test, is that you basically run the same simulation over and over again on different meshes. And so you typically start with a fairly coarse mesh, so with very, very few number of elements, and then you run the simulation and you record the results. And then you kind of successively kind of increase the resolution of the mesh. And then you rerun the same simulation, and you look and see how your simulation changes. And then eventually, once you refine the mesh to a certain point, if you refine the mesh even more, then the simulation results aren't going to change. And so at that point, you've reached what's called mesh convergence. And at that point, you basically say that your simulation no longer depends on the mesh, and you've reached kind of the maximum amount of accuracy that you can with the mesh. And so, if you're going to do any kind of, I would say kind of technical reporting or any kind of research with finite elements, a mesh convergence test is almost necessary, because that's always the first question people ask, is that, is this mesh accurate enough for what you're trying to accomplish? And so mesh convergence test is kind of the way or the best way to kind of determine that. We'll talk about that a lot more kind of later on in the course. I don't think it's going to be part of your midterm project, but it will be part of your final project. And so we'll talk about it kind of closer to that. Okay. But kind of for now, the only thing you have to kind of keep in mind is that, this kind of relationship between cost and accuracy. So, a mesh, when you're choosing your mesh size, you kind of have to do it a little bit thoughtfully, just knowing that when you make the elements smaller, you are increasing the cost, you are increasing the accuracy, but you're also increasing the cost at the same time. Okay. All right, any questions on this? All right, so let's talk about element shapes. Okay. And so just like, I alluded to earlier, when you're creating a finite element mesh, you can choose, you have some kind of latitude in terms of what shapes that you can choose for your finite elements. In reality, in theory, almost any shape can work as long as you can write the algorithms for it. But for most practical situations, we kind of have I would say two categories of shapes that you can choose. Okay? And so I call them categories because, they have kind of a 2D version for it and a 3D version, but they kind of have very similar behaviors. Okay? And so the two categories are the triangular shapes and the rectangular shapes. Okay. So let me draw a table here to kind of show you kind of their differences. So there's a 2D version for these and a 3D. First column here, we'll do triangular shapes. And then on the right will be the rectangular. Okay. Okay, so let's start with a 2D triangular shape. Okay. This was pretty straightforward. So a 2D triangular shape is literally a triangle. Okay. And then the rectangular 2D shape is a rectangle. Big surprise. Okay. But we usually call this rectangle a quadrilateral because it has 4 sides and 4 coordinates.
Dr. Chan.
Yep.
So this popped up into my head seeing those two drawings. Is it safe to say that a triangle is more accurate than a rectangle because it's half a rectangle, quote unquote?
Not necessarily.
Okay.
Not necessarily. So we'll
Okay.
talk about their differences soon. Yeah.
That sounds
Let me
good.
get through the 3D one and we'll talk about kind of where the triangular shapes are better than the rectangular ones, because
Sounds
they're
good.
in certain situations. Okay, so the 3D triangular shape is a 4-sided pyramid. And so this is often called a tetrahedron. And the 3-dimensional rectangular shape is a box. Some people call it a brick. but we call these hexahedrons. Hexahedron because they have 6 sides, basically. Okay. All right. And so these are kind of your options when you're choosing element shapes within ANSYS. So, I think a lot of custom codes have the ability for other shapes, but generally this is kind of all your options. Okay. And so what are the differences between these shapes besides their visual differences? Okay. So let's talk about the triangular shapes first. And so this applies to both the 2D triangle as well as the 3D tetrahedron, okay? And so the really nice property about triangular shapes is that they have what's called the simplex property. And so what that means is that if you wanted to, you can take any geometry, literally any geometry, and you can mesh it with triangular elements, okay? You guys have a question over there? And the reason for this is that, like I mentioned, this is something called the simplex property. And so what that basically means is that you can fill any space with triangles.
Dr. Chan, can you please write that down? The simplex property?
I'm writing it down right now.
Thank you, sir.
Okay. All right, so how can we take advantage of this? And so, from a practical perspective, we can take advantage of this whenever we have a very complex geometry. And so if we're doing an FEA simulation, our geometry is very complex. It has a lot of fine features, it has a lot of twists and curves and things like that. Normally, you're going to want to start with the triangular mesh because what that mesh is going to do is that it's going to match your geometry exactly. And so, sometimes what you'll see in ANSYS is that even if you specify one of the rectangular elements, so let's say that you want a hexahedron mesh, if it's really struggling with it, you might interpret it as like ANSYS is disobeying you and putting a triangular mesh when you tell it to do a hexahedron mesh. That's not necessarily the case. That usually happens when ANSYS will try its best to do a rectangular mesh, but the geometry may be complex or maybe the size might be too big, where it wasn't able to do that, and so it just defaulted to triangle. Okay.
Dr. Chan,
Yeah.
Is it ever possible to use triangles and rectangles in the same mesh, both of them?
Yeah, of course. Yeah, we'll talk about that
is?
later. So that's something
very
called
nice.
mixed meshing, and so you can definitely mix different element shapes and even different element sizes in different parts of the geometry.
Can you please say what that is called again?
It's called mixed meshing. So we'll talk about it
mixed
later in the
Sounds
class.
good.
Yeah.
Thank you, sir.
All right, so triangular meshes, triangular meshes are always a good starting point. So, usually kind of when you're first making an FEA, doing a triangular mesh is usually not a bad idea. Then you're almost guaranteed to get a mesh out. Okay, and so when would you want to use a rectangular mesh as well? Okay, so rectangular elements, their benefit is that they fill space very efficiently. And so because they're kind of naturally just a little bit bigger than triangles, you know, if you keep the mesh size fixed, you'll get a mesh with less elements using rectangular versus triangular. Okay, so it's much more efficient at filling space. Another nice thing about rectangular elements is that they have a lot of very nice solution properties on them as well. And so basically the way we can say that is that the FEA algorithms just naturally get a more accurate solution on rectangular elements versus triangle elements. Okay. And so what this means, so kind of the upshot of kind of both of these things together is that you can get a more accurate simulation with less rectangular elements compared to triangular elements.
Is that all for complex geometries?
Right, so we'll talk about that in a second. So kind of the caveat with rectangular elements is that you're not able to get a mesh using rectangular elements all the time. And so generally, if you have a complex geometry, you may be able to do some parts with rectangular elements, but you're not going to be able to do all of it with rectangular elements. And so, use it. And so generally, if you can use rectangular elements if you can, but then sometimes you're just not able to because the mesh just isn't it's not able to form.
So from my understanding, some simulations work with rectangles and some work with triangles and some work with both.
So generally, if you have a geometry that can lend itself well to rectangular elements, it's generally preferred to use them because you're going to fill the space with less elements. You're going to get a more accurate solution, and it's going to cost less.
Thank you,
and so
sir.
rectangular elements are good when you can use them, but you're not able to use them on every geometry because the mesh you'll see and some of you will run into this actually in activity too. You're going to try to put like a hexahedral mesh on the geometry, and ANSYS will just say that the meshing will fail.
And if that happens, how do we fix that? Do we switch to rectangles or do we decrease the number of elements in the hexa?
So you can decrease the element size. So that's one way you can do it. So part of the reason it fails is because if your rectangles are kind of too big, it's hard for the FEA to kind of squeeze that into your geometry. So one thing you can do is you can reduce the element size. The other thing you can do is you can switch to triangles. And so switching to triangles will make it a lot easier to mesh.
I see. Thank you, sir.
And so kind of the upshot is that, if you can, And generally the types of geometries that work well for rectangular elements are geometries that look rectangular. And so if you have boxy kind of elements with kind of straight faces, straight edges, that generally tends to be easier to mesh with rectangle. But if you have a lot of curved edges, a lot of kind of sharp corners, rectangular elements kind of really struggle in those cases. And so, it's something that I think if you try to describe it with words, it ends up being kind of very kind of general, kind of like what I did now. But kind of as you start to use it more, and so as we go through the activities this semester and as you do the projects, you'll start to get a sense of, this geometry will work with rectangles, this geometry won't work with rectangles. And so, it's something more of a feel kind of thing. So, as we kind of go through the semester, you'll get a general feel for it. But, I wanted to kind of introduce it now, just so that you have kind of the idea of it and kind of the trade-offs between the two shapes. Okay. Any questions on this? Okay, so let's talk about mesh quality or skewness. Okay. So quality is a very specific definition, and so you could argue that we can talk about mesh quality all day today, right? But when someone mentions mesh quality, they specifically are talking about the quality of each individual element. So actually, after you produce a mesh, what a lot of softwares will go and do is that it'll rate each element in terms of how good it is. Okay, and so what does that mean? And so the quality of an individual element refers to its dimensions, basically. It refers to its exact size. And so generally speaking, the ideal kind of element, kind of the perfect element that you can imagine is very balanced. And so what I mean by that is it's the length of its sides, if it's in 2D, or the size of its faces in 3D are all roughly the same. So in other words, the perfect triangular element would be an equilateral triangle. Look. This is a high quality triangle. Okay. And so all the edges are roughly the same size. The interior angles of the triangle are all roughly the same. Okay. And so this would be a high quality. Okay. A poor quality triangle might look something like this. So it might look very skewed. And so you might have two edges that are extremely long, okay, and then one edge that's really short. And so I would say this is a highly skewed triangle. So there's three-dimensional versions for this too, and they're highly skewed rectangles as well. But generally speaking, for a high quality solution, you want high quality elements. Okay, and so ideally, Because what can tend to happen for the highly skewed triangles or highly skewed element shapes is that they tend to produce kind of weird irregularities in the symmetry just because of how skewed they are. Because you have, maybe some edges are significantly longer than other ones. And the one I drew here actually this is actually not that bad. Even though obviously it's very different from the equilateral one. You can have some meshes that have elements that have edges that are up to 10 or even 100 times bigger than its shortest edge. Okay. And so the way that you can rate this, because whenever you produce a mesh, it's always good to check the quality of the elements. You can actually use ANSYS to check the quality, and ANSYS actually does a very nice job of this. Okay? And so there's lots of different metrics for quality. And so there's lots of different things that you can do, but generally the one that I like to use is something called skewness. Right? And so what ANSYS will do is that after you produce a mesh, it'll look at every single element in the mesh and produce its skewness score. Okay. And so the way to read the skewness score is something like this. So if you have a skewness of about 0, a skewness of 0 means that the element is high quality. And so generally you would want a skewness of 0 for every element. And so the maximum skewness score is actually 1. And so the skewness is going to vary between 0 and 1. And so a skewness of 1 means that the element is highly skewed. So it's about as skewed as it can be. And so I'll show you this on Wednesday. So when you produce a mesh, there's kind of a tab in the meshing properties for the quality. And so we can actually view the skewness of all the elements. Okay. And so whenever you produce any mesh, unless your geometry is a perfect box or a perfect triangle, there's going to be some skewness. And so it's unavoidable because there's always going to be kind of a weird spaces in the geometry that get produced when you're producing the mesh. And ANSYS is going to have to squeeze an element or two into that weird space. And so some skewness is unavoidable. So don't try to totally eliminate skewness. But you can try to achieve kind of certain benchmarks for the skewness. Okay, and so when you view skewness in ANSYS, it'll tell you kind of it'll give you 3 numbers generally. So it'll give you the maximum skewness, which is it'll find the element with the maximum skewness and give you that skewness score. It'll give you the minimum, and it'll give you an average. And so the ones that we really care about are the max and the average. And so for the max skewness, and these are kind of both kind of rules of thumb. These are kind of my own personal rules of thumb. But depending on your application, it might be different. So a max skewness of about maybe about 0.9. If it's less than 0.9, I'd say that's usually pretty good. And if your average skewness is less than about 0. Either 0.5, between 0.5 0.6 is usually pretty good. So I'll say less than 0.6. And so if you can kind of reach these benchmarks, that means your mesh is in pretty good shape. And so going back to our element shapes a little bit, one of the nice benefits of using a rectangular element mesh is that those tend to not skew themselves all too much. Okay. So for triangles, even though, yes, the triangle was able to mesh any geometry, you might end up with a situation where you have a few triangles that are very highly skewed. Okay. So rectangular mesh generally doesn't tend to do that. But the bad side is the rectangular mesh will just kind of just give up before it reaches that point. And so a rectangular mesh is, sometimes it'll fail. And so you might never reach a situation where you have a highly skewed rectangular mesh because it may not even mesh to begin with. Any questions on this? Yeah.
Does it create a heat map of the skewness?
I think you can set it to be, but generally the only thing you really need is just the max and the average. But there are ways that you can view heat map, and that can be useful where if you're getting mostly highly skewed elements in a certain area, then that'll tell you, you need to work on the mesh in that area. Exactly. Yeah. Okay. We may not get to mixed meshing today, but I did want to talk about element order before we go for today. And so another consideration that you have to make for the mesh is its order. Okay, this one's a little bit harder to explain without diving really deep into the theory. So for those of you who have taken 541 with me, you probably kind of know exactly what I'm about to say regarding order, but without really going to the theory, it's a little bit hard to explain. But I'm going to do my best to kind of give the 10-minute or the 20-minute version of element order. Okay. And so when you're solving an FEA problem, we know that FEA is an approximation to an exact solution. Okay. All right, and so we know that whenever we solve an FEA, there's an underlying differential equation, and FEA is going to solve for an approximate solution to that equation. Okay. All right, and so the way it accomplishes this is that it kind of solves the equation in reverse. And so usually when you solve an equation, you usually look at the equation and then you go through a method and you get the solution from there. The way FEA works is that it looks at the equation, it assumes a form of the solution, and then it finds the best solution that fits, that can solve that equation. Okay. So there are two forms that we basically usually work with in FEA, especially in ANSYS. And one form is a linear polynomial. And the other is a quadratic polynomial. And so, in reality, you would have kind of a 3D linear polynomial and a 3D quadratic, but just for the sake of, simplicity, I'll just do 1D version of this. And so a 1D linear polynomial, we'll call it u of x. We'll have a constant term as well as a linear term. Quadratic one, u of x will be a0 plus a1x plus a2x squared. And so FEA is going to assume one of these forms of the solution and then finds the best version of this assumed form that's going to solve the equation. Okay. All right. And so, when you're running an FEA simulation in ANSYS, you can actually choose, the assumed form of a solution. Okay. And the way that you choose that is you choose the element order. And so the choices that you have for element order are either linear or quadratic. And so generally speaking, the choice for this is, it goes a lot deeper than this. And so there's a lot of theory behind, element order and what effects it has. But generally it kind of boils down to two things. And so the linear order is generally cheaper. Okay. And so if you choose linear elements, it's going to be faster to compute. Okay. But there's no free lunch, and so generally a cheaper solution means that it's also less accurate. So quadratic must mean the opposite. So quadratic order generally is going to be more expensive. Okay. But it leads to a more accurate solution.
Dr. Chan.
Yeah.
So you having presented this information to us, I'm assuming that we use linear order for linear cases, obviously. For nonlinear cases, is that to say that we would use a quadratic order for nonlinear cases?
Actually, generally for structural simulations, most of the time you're going to pick quadratic order.
Okay.
And the reason for that is that there's some other issues that can happen in structural simulations, and so I'll write this down in a second. But in structural simulations, you can have something called shear locking,
Okay.
which basically is if you have a linear element and your mesh resolution isn't high enough, then the elements can literally lock up on themselves, and you'll get a solution with a very small amount of deformation, a very kind of mysteriously small amount.
I see.
Kind of the way to kind of avoid that is to use a quadratic order.
I see. Thank you, sir. I don't want to waste any class time, but I'm thinking about nonlinear cases. Is there anything we could, is FEA used for nonlinear cases, or?
It is, yeah, and we'll be going over that later on in the course too. So
Okay.
I think we have a week where we're talking about nonlinearities in FEA, kind of what those mean and how we deal with it. Yeah. And for those cases, you definitely want to use quadratic elements because the
sounds good.
Yeah, because the linear elements are not going to be able to capture it.
Sounds good.
Okay, let me give you kind of a visual representation, just because it's it's one thing to kind of talk about it, but it's easier to kind of visualize. Okay, let me draw two curves here. So let's say that let's say that we have a solution that we're trying to emulate. Okay, I'll draw the same thing on both graphs. Okay? And so in red right here, we'll assume that this is a solution to the differential equation that we're trying to emulate. Okay, so we'll call this the exact solution. And so if you were to solve the equation by hand, you would obtain what's in red right there. I just have to tell myself to not use red and green because red and green color bias. Okay, all right. And so in blue right here, what I'm going to draw is what you would obtain with an FEA solution. Okay. And so on the left right here, we're going to draw a linear FEA solution. Okay. And so a linear FEA solution, what that's going to do is that it's going to assume that your solution in this region is a linear function. The linear function just looks like a line. So it basically would look like this. Okay. Whereas on the right here, I'll kind of illustrate kind of what a quadratic FEA solution looks like. Okay? And so the main benefit that you get for using a quadratic order is that your solution could actually have some curvature to it. So that's literally impossible with a linear function. Okay. And so maybe we don't match this exact solution exactly, but we may get pretty close. So maybe we have a solution that kind of looks like this. Okay. And so because of the quadratic term in the assumed solution, you can have some curvature in the solution. So you end up kind of being more exact. Okay. The downside is that a quadratic element is roughly about 50% more expensive than a linear. So sometimes you have to be a little bit careful about this. Okay. And so let me make a special point with regards to structures. Okay. That's what we're going to be doing mostly in this course. So this is true for excuse me. This is true for structural FEA, but it's also true in general for any differential equation that relies strongly on its derivative. Okay. Okay. And so in these situations, you have to be careful using linear elements. Okay. Okay. Because linear elements can lead to this phenomenon known as shear locking. Okay. So shear locking, visually what it looks like is that if you have shear locking occurring, it looks like your system is locked up. So you're going to have deformations that are very, very small and stresses that are also very, very small. Okay. And so the reason this happens, and the reason it happens specifically for linear elements, is because of the fact that when you take a derivative of a linear function, you end up with a constant, right? And so why is that an issue? And so that's an issue because in structural FEA, remember we talked about last Wednesday, is that there's a very strong relationship between the stress and the strain inside a structure. Okay. And so how do we compute strain? And so strain, the way that we compute it is we take the derivative of the deformation. Right? If you have a linear element and you have a constant derivative, that means that the strain is going to be constant within the element. And if the strain is constant, that means the stress is constant within the element as well. Okay. So I'll kind of give you a visualization of why that's an issue. So let's say that we're doing a simulation of a beam. Say I've broken up the beam into elements like this. Okay. Normally, to load this beam, let's say that we apply a force on the end. And so what's going to happen is that this beam is going to deflect, right? And so you apply a force at the end. We know the end is going to tip downwards. Okay. And what's causing that, or kind of the relationship that we're kind of tracking with the equations, is a relationship between stress and strain within the beam. Okay. And so what you should see normally is kind of a variation of stress. And so the stress should be the highest here. Okay. And then as you kind of go down the beam, the stress will kind of gradually decrease. Okay. Except it's not really like the relationship's not really like that. So what you're going to see normally is something like this. So you're going to have kind of a very high stress at the fixed support, and that's going to drop off very quickly. Okay. So this is stress versus distance. Okay. What happens is that if you have a linear element, and you have an element that kind of is in this area, kind of like that, okay, you can see here that as you go from one end of the element to the other, the stress in reality varies quite a bit, okay? And that variation of stress is kind of what drives the deformation. But if you have a constant stress element, you may estimate the stress as something like this. And if you estimate that stress is that something that's that low, we're getting a very inaccurate result, because what we should see is that stress varies a lot throughout the element, but we're completely missing that with the linear element. Okay. But if you were to have a quadratic element, you could at least have some variations. Maybe the stress, might go like this. Okay. It's still not perfect, but at least you have some variation. So, when you have variation of stress within the element, it's much less likely to lock. And so for that reason, when you think you're going to have an area of kind of high stress change, and so if the stress is varying very rapidly, you want to use a quadratic element just to make sure you can capture that change in stress. Okay. All right, any questions on this? Okay. All right, so one last thing. We do have 5 more minutes, so I think that's enough time for mixed meshing. Okay. Let's talk about just this idea of mixed meshing. Okay. And so we've talked a lot today about all the different settings that you can have with a mesh. And so, we first talked about the size of the elements, then we talked about the shapes, and then finally we talked about the order. Okay. And so there's a lot of decisions you have to make for the elements. And, for a lot of cases, there is a preferable choice, right? So generally, we generally prefer rectangular elements and we prefer quadratic. Okay? But there might be situations where there are certain parts of your geometry where you want to make one choice, and other parts of the geometry where you want to make another choice. Okay? The beauty of using kind of a commercial software like ANSYS is that it's very easy to kind of mix and match different mesh settings for different parts of your geometry. Okay. So to accomplish this, you can use a lot of the settings and a lot of the tools that we use in the first activity. Okay. Okay. And so if you want to change the shape or the order of the mesh in a particular area, you would use a method object. Okay. So the method will let you change those things. Okay. The other main one that you'll use is the sizing object. So the sizing object will let you specify a different mesh size in a certain region. Okay. And there's some examples of cases where you would want to use this. So let's say that you have a particular area of the mesh or particular area of your geometry where you want to have higher accuracy. Okay. And so some situations where you might want to do this are, maybe you have regions of your geometry where you have a high amount of stress concentration, or maybe you have regions in your system where your solution is changing a lot. Either you're having, rapid changes in deformation or rapid changes in stress. Okay. Usually you want to pack those areas with a high amount of elements just to make sure you capture that change very accurately. Okay. For example, is that maybe you have, different parts of your geometry with different geometrical features. Okay. And so, like I mentioned earlier, you may have a region of your geometry that's very, blocky. Okay, so you might think that rectangular elements are probably going to work out in this area, whereas you might have a region of your model with very lots of curved edges, and maybe you want to use triangles there as well. Okay, right. Other situations you might have, or maybe there are parts of your geometry where you don't really care about the accuracy all that much. Okay, and so you might choose to coarsen up the mesh in those areas to reduce the cost. Okay. Or maybe there are certain parts of your geometry, you want to reduce the order as well, kind of the same. All right, any final questions on any of this before we wrap it up for today? Okay, all right, so actually that, I think this is a good time to stop. So this just about covers the basics of meshing. So we covered mesh size, shape, and order. And so, we'll put those in practice on Wednesday. Okay? remember, Wednesday is going to be our next ANSYS activity. And so remember, for the activities, you're free to continue attending online, but generally I help. It's easier for me to help you in person to help you keep up there. And so Wednesday would be a good time to come in person if you're able to. But of course, I'll do my best to help you out over Zoom as well. Okay? All right. So thank you guys for coming today. Hope you guys enjoy the rest of your night, and I'll see you on Wednesday for our next ANSYS activity.
Thank you, Dr. Chan.
Thanks, Ivan.
Oh, Dr. Chan,
Yep.
I actually have a question. So for the ANSYS activities, are you going to make the activities available to us students via Canvas when class starts, in case any of us can try to get ahead while you're doing lecture, and if we get stuff we could ask you? Does
Yeah.
that make sense?
I'll post the activity in the PDF on Wednesday afternoon. So
Oh,
we can even
perfect.
get started early before the course. If
Perfect. Thank you so much, sir.
Yep.
Okay.
Dr. Tran. Dr. Tran. Can you hear me?
Yeah, I can hear you. What's
Okay.
up, Chris?
Which Dr. Tran do I send the direct message to?
You can send either one. So one's my iPad and one is
Well, is
maybe
it
do
going to
the one
show up
that's
on the video?
let me kill the video.
Well, I'm just wondering.
Okay. Yeah.
Yeah, I was gonna
Yep.
let me send it. Is that the right one? I only asked because you were talking about putting the answers out. Yeah. Okay. Good night.
All right. Any other questions, Chris, before I sign off?
No, I'm good. Good night. Can you hear me?
Okay. Oh, I see your mic going, but maybe I turned off the projector, so maybe the sound's not coming out anymore. Okay. I don't think I can hear you though. Did you have any other questions? Okay. All right. Have a good night, Chris. I'll see you Wednesday.